This is Thursday, February 18th, 2021, recording class session for Physics CP on circular orbits. One of the first skills in basic orbital mechanics is to be able to calculate circular orbits. So in a previous class, I'd already worked out some formulas and equations. I just want to begin by repeating that list that says, if I have an object going around in a circular orbit of radius r and it's going at speed v, then the period of time that it takes for it to go around once, we represent that with capital T. R is called the orbit radius, and you need to be careful not to mix that up with the radius of the planet, or central body, as I'm going to refer to it. V is the speed, and there are several equations that come out of this. So one of them is, and all this is for circular orbits. The speed squared is the product of the universal gravitational constant times the mass of the central body divided by r. Again, r is the orbit radius, lowercase r, orbit radius. G is a constant. Its value is 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. The period for all of our calculations has to be converted into units of seconds. And the orbit radius has to always be converted into units of meters. So I'm going to talk in kilometers, but then you have to remember, 1 kilometer is 1,000 meters. And it's up to you to figure out how many seconds are in a minute or hour or day or year. So here's one equation that relates the speed at which you're going around the circle with the mass of the central body and the radius measured from the center of that object to your location in your orbit. A second equation is Newton's law of universal gravitation minus gravitational constant times the mass of object 1 times the mass of object 2 divided by the radius squared. And it's occurred to me, I probably didn't even cover this equation with you, this first one. Yikes. In fact, here in CP physics, what we did was centripetal force was m times v squared divided by r. And of course, centripetal acceleration is v squared divided by r. Yep, so I'm sorry, I didn't even cover this equation with you. What we have so far is the centripetal force and Newton's law of universal gravitation. On your homework, I have you do calculations of just the different masses. All right, so for Physics CP, we're at the point where we've had the formula for centripetal force and Newton's universal law of gravitation. And as an example, here's a problem. We have a brick of a given mass moving in a circle with a given speed and a given radius. And the question is, what is the centripetal force on the brick? So let's just make up a different problem that has much the same numbers or ideas. So I have a mass, and this mass is 12.0 kilograms. And it's moving at a speed v of 14.0 meters per second. And it's in a circle of radius 3.50 meters. And the question is, what is the centripetal force on this object? Okay, what is the centripetal force? To solve that problem, at the moment, we only have two equations to look at. Either the law of universal gravitation or the centripetal force equation. So, of course, select the centripetal force equation. Centripetal force is the product of mass times velocity squared divided by r. In this case, I would plug in 12 kilograms times 14 meters per second squared divided by 3.50 meters. Okay, I agree with my students. The centripetal force in this example worked out to be 672 newtons. If I had given you the time in kilometers per hour, then you would have needed to convert the kilometers to meters and convert the hours into seconds before you could plug it in. If I'd given you the distance in centimeters instead of meters, then you'd have to convert it to meters before you plug it in. Okay, so I'm hoping that's enough review on these two equations, three if you want to count acceleration. Newton's law of universal gravitation, centripetal force, centripetal acceleration. Now, interestingly enough, I'd like to move on and give you a formula for calculating the acceleration due to gravity on the surface of a planet. So imagine that this is the Earth. And not to scale, there you are on the surface of the Earth. If I were to ask you to calculate how much you weigh, you would say, oh yeah, the force of gravity, my weight, is the product of my mass times the acceleration due to gravity. But wait, Newton's law of universal gravitation will also calculate the force of gravitational attraction between you and planet Earth. That equation says the force of universal gravitation between any two objects in the universe is equal to the product of the universal gravitational constant times the mass of one object, in this case the Earth. I'm using the old astronomical symbol for the Earth, capital M for the mass of the Earth, times the mass of you divided by the distance from you to the Earth squared. Now, you might look down at your feet and falsely think that the distance from you to the Earth is 0 meters. But when we measure the distance to be used in this formula, it's measured from the center of one object to the center of the second object. And so the Earth has a radius, which I'll write with capital R, of the radius of the Earth is 6,378.14 kilometers. And if you are standing up on the Earth, you might add about 1 more meter to that, to the center of your mass, and not even a whole meter. So what is that going to do? That would be way out here, 2 more decimal places to the right, after I've already listed this to 6 significant figures. Your height would be out in the 8th significant figure, if that. Maybe 9th, now that I think about it. Yeah, 8th or 9th. 8th. In other words, it is sufficient as long as you're standing on the Earth and you're not large compared to the size of the Earth to just say that the distance from the center of the Earth to the center of you is the radius of the Earth. Okay, well, this formula will calculate the force of gravitational attraction between you and the Earth. This formula is what we use to calculate your weight when you're on the surface of the Earth. These two are the same quantity that we're calculating. In other words, I can take your weight, mg, and say that is what we get when we do g mass of the Earth times your mass divided by the radius of the Earth squared. In other words, your mass can cancel out. And we're left with an equation that says the acceleration due to gravity on the surface of any planetary body is the product of the universal gravitational constant times the mass of that body divided by the radius of that body squared. Ta-da! So we should add this to our list of equations that we can use to calculate, in this case, it relates the mass and radius of an object to the acceleration due to gravity on the surface of the object. So let's do an example. Suppose I have an asteroid or a comet. Yeah, an asteroid. And its mass is, bigger than a car, bigger than a skyscraper. So let's make it maybe 1, 2, 3, 0, kilograms. And this chunk of space rock, I don't know what would be a proper density for it, but let's say it's roughly spherical in shape and that it has a radius of, let's just make up a number and say 150 meters. Some planetary scientist somewhere is going to calculate the density of this and cringe and say, wow, that was terrible, Mr. Turek. But, okay, so let's say it exists anyways. Maybe it's hollow. Maybe it's filled with something dense. Whatever it is, in this, I would say hollow. Whatever it is, if you were to stand on the surface of it, what would be the gravity pulling you to the center of this little asteroid? The answer is you plug it into the formula. Capital G times that mass divided by that radius squared. All right, pause this recording and calculate it. Okay, so the result is 3.65 times 10 to the negative 10th power meters per second squared. Very, very tiny for this small asteroid. Okay, so resuming what we have at the moment, we have Newton's law of universal gravitation. We have centripetal force. And by the way, I think I could probably also rewrite this one as m times 4 pi squared r divided by t squared. Not sure if I've done that one for you yet. A sub c is equal to v squared over r, which is equal to 4 pi squared r over t squared. And this latest one, g is equal to capital G m over r squared. Yikes. So let me remind you on these two, because I'm not sure I had done that recently. If I have a circle of radius r and I'm moving at speed v, and it takes a period of time t to go around the circle once, well, the speed that you're traveling is equal to the total distance that you travel, 2 pi r, divided by the time that it takes to travel that distance, capital T. The speed at which you're traveling in a circle is equal to the circumference divided by the period of time it takes to go around once. So if I substitute 2 pi r for v into the centripetal acceleration formula, then I have a sub c is equal to 4 pi squared r divided by t squared. Because as we established in a previous class, one of the r's will cancel, so that's why it's not r squared here. And if this is centripetal acceleration, and centripetal force is mass times centripetal acceleration, then I can also say that the centripetal force is 4 pi squared r over t squared, all that times m. Whether you want to put the m in front or afterwards, there it goes. All right, so we have this collection of equations, and now I want us to start applying this to spacecraft that are orbiting objects. Okay, we haven't been in orbit yet. Kind of a big step. It goes like this. Consider the sun. And here's the Earth, and it's going around and around the sun. And it's been doing that for billions of years, by the way. This is a circle. And as you look at the circle, there's got to be a centripetal force making the Earth not go fly off at a tangent. As the Earth goes around in a circle, if there weren't a force acting on it, then by Newton's first law, the Earth would just continue moving in a straight line at a constant speed. This centripetal force, we can calculate how much it has to be based on what we know about the circle. Well, what do we need to know? We need to know the mass of the Earth. We need to know the radius of the Earth's orbit around the sun. We need to know the time period it takes for the Earth to go around the sun. And if we have all of that, then we can calculate the centripetal force from this formula here. 4 pi squared r over t squared times the mass of the Earth is the centripetal force acting on the Earth. So here's some numbers. The mass of the Earth is 5.974 times 10 to the 24th power kilograms. The radius of Earth's orbit around the sun is 149.6 million kilometers. Let's see. 6, 7, 8, 9, 10, 11. Yeah, okay. And the period of time that it takes for the Earth to go around the sun once, no, it's not 1 day, it's 1 year. Exactly 1 year. Well, so how much is 1 year exactly? That's the question. So we're going to use 365.25 days, which is pretty close to an actual year. Okay. Well, calculate what would be the centripetal force acting on the Earth. Okay, so pause this video and do the calculation. All right, so I accidentally wrote F sub g when I should have written F sub c. The centripetal force is what we're calculating. And the formula is m, the mass of the Earth, times the centripetal acceleration, which I'm going to use the formula that says 4 pi squared r divided by t squared. The numbers I'm going to plug in are 5.974 times 10 to the 24th power kilograms times 4 times pi squared times 1.496 times 10 to the 11th power meters, because 149.6 million kilometers, million is 10 to the 6, kilometers 10 to the 3, 10 to the 6 plus 10 to the 3 is 10 to the 9th. Now move the decimal point 10 to the 10th, 10th to the 11th power. So 1.496 times 10 to the 11th power is the number of meters from the center of the Earth to the center of the Sun on average. And the formula says now take all that in the numerator and divide it by 1 year squared. But the year has to be in seconds. So I would go open parentheses, 365, whoops, I wrote 2. 365.25 days. Oh, and I see the problem here. I wrote 2 earlier as well. 365.25 days times 24 hours in a day times 3,600 seconds in an hour will convert 1 year into seconds. And then when you're done, square it. The answer I got, maybe I should do it a second time. Assuming I typed it all in correctly, I get the same result as before. I have a centripetal force of 3.54 times 10 to the 22nd power newtons. That is the centripetal force needed to make the Earth continue to go in a circle around the Sun. Oh, but I'm not done. My next question is, what is the force of gravity between the Earth and the Sun? And for that one, we're going to use Newton's law of universal gravitation. G m1 m2 over r squared. R and the mass of the Earth are given. So now we just need to know what is mass of the Sun. And Lord Google says right away, the mass of the Sun, and I forget the symbol for Sun, is 1.989 times 10 to the 30th power kilograms. So now, calculate, please, what is the force of gravitational attraction between the Earth and the Sun? Pause the video, do the calculation. All right, so when we plug in all the numbers, it's going to be 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. That's the value of G, capital G, times the mass of the Earth. And it doesn't matter which one you do first because we're multiplying them. So I'll just list the mass of the Earth. 5.974 times 10 to the 24th power kilograms times the mass of the Sun, which is 1.989 times 10 to the 30th power kilograms. And now we're going to divide that by the distance from the center of the Earth to the center of the Sun squared, which is 1.496 times 10 to the 11th power meters, quantity squared. Beep, beep, beep. The force of gravitational attraction between the Earth and the Sun, I get 3.54 times 10 to the 22nd power newtons. Ta-da! That is not a coincidence that these two numbers work out to be the same. So let me try to guide you in understanding why that makes sense. Consider the Sun and the Earth going around the Sun in its orbit around the Sun. If the force of gravitational attraction between the Earth and the Sun, Fg equals G m1 m2 over r squared, if that were greater than the centripetal force mv squared over r, then what would happen is it's saying that the force of attraction is actually greater than the force needed to keep us in a circular orbit. And so the Earth would spiral in towards the Sun, and we would all burn up and die. If the gravitational pull between the Earth and the Sun were less than the centripetal force needed to keep the Earth going in its orbit around the Sun, if this gravitational pull was too weak, then the Earth would go spiraling out away from the Sun, and we would all freeze to death and die. So you might notice that what's common here is that we're not dead from burning up or freezing to death, with possible exception of people in Texas. Okay, so for 5 billion years at least, we haven't died one way or the other. From that, you should have the light bulb turn on and say, hey, these two equations must be equal to each other in their strength. mv squared divided by r, the centripetal force, must be equal to G m1 m2 over r squared, the gravitational force of attraction between these two objects. Here's the mass of the Earth, here's the mass of the Earth, and the mass of the Sun. So we can cancel out the mass of the Earth. We can also cancel out one of these two radii. Here it's divided by r, here it's divided by r squared. So if I were to multiply both sides by r, then the r on the left is completely canceled, and one of the r squareds on the right is canceled. And this leads to v squared, the speed of an object in a circular orbit around a planetary body or central body, is equal to capital G times the mass of that central body divided by r. Okay, let's make up an example. I have an asteroid with a mass of 345 times 10 to the 10th power kilograms. I'm just making that up. My phone is very busy today. So that's a comma there. All right, 345 times 10 to the 10th kilograms, which of course means 3.45 times 10 to the 12th power kilograms. So I have a small asteroid. And I am orbiting this asteroid at a distance r of, let's say, 3, that's strange, isn't it? 3.70 times 10 to the third, fourth, fifth power meters. 370 kilometers, right? That's 370 kilometers is my orbit radius. 3.70 times 10 to the fifth meters. And I ask you, so what would be the speed at which I'm orbiting this little weak asteroid? And the answer comes from this formula. My speed would be the square root of gm over r. And so the numbers I would plug in, 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared times 3.45 times 10 to the 12th power kilograms divided by 3.70 times 10 to the 5th power meters. Calculate, please. What is my speed? Okay, so finally, my students and I calculated the result is 0.02. Now that's only one sig fig, and we should do this to 3 sig figs. So the next digit would be 4, and the next digit should be 9. That is 3 sig figs, meters per second. When you're far from a small asteroid, you're not going to be orbiting it very fast.